Okay, good morning, everybody. So we're moving into part 2 of the course, where we actually start the object-oriented part of the course. So you're going to start to implement your own classes moving from this point forward. So before we start this part, I just want to review some fundamental terms that are used to describe, well, that are used in object-oriented programming languages. Right, so first of all, we have the notion of a type. Right? So a type is a set of values and the operations that you can perform with those values. Right? So you know what an int is, right? Everyone knows an int is just an integer value. It has a maximum value. It's got a minimum value. Right? You can do things with an int like add, subtract, divide, and so on and so forth. Right? We've seen string. Right? So string represents a sequence of characters. Right? And what can you do with a string? Well, you can do things like compare two strings for equality. You can ask a string for a character. Right? You can get a substring from a string, and so on and so forth. Right? The set of all strings is basically the set of all sequences of 0 or more characters. And finally, we know what a list is. Right? So a list, you know, is a sequence of 0 or more elements. And in Java, they're elements of the same type. Right? What can you do with a list? Well, you can compare two lists for equality. You can get something from a list. You can set an element in the list. Right? And you can compute a sublist of the list in Java. Right? Or get a slice if you want to think about it in terms of Python terms. Right? So that's what a type means. Right? You know that there's primitive types in Java. Right? So there are the 8 primitive types. We've seen these before. And you know that there are reference types. So anything that's not primitive is a reference type in Java. Right? So arrays are reference types, even if they're arrays of primitive values. Right? So an array of int is considered a reference type in Java. Right? So you know that a string is a reference type, a list is a reference type, an array list is a reference type, and so on and so on. And in fact, in Java, most things are reference types. And so how do you get these reference types? Well, you define a class. Right? And that's what we're going to be doing moving forward. Right? So a class is just an implementation of a reference type. Right? So in Java, a class is also a type, right? But not every type is a class. So we saw interfaces the other day, and, you know, that and I told you that an interface is also a type. And it's a reference type. Right? So for example, string is a class. Right? Array list is a class. Right? But list is not a class. Right? List is an interface. And an object is just an instance of a class. Right? So the way you make an object is you take the class and you use the class as a blueprint, and you make objects using that blueprint. Right? So for example, I can make an array list, right? A new array list. So what that does is it creates an array list object using the array list class as a blueprint to make that object. Okay, now finally, what's a reference? So a reference is an identifier that you can use to find a particular object. Right? So if you came to the lab last week, then we saw that when you use the debugger, you can actually see references to objects, right, when you run your program. Right? And the debugger shows it to you as this thing called ID. Right? It turns out that in most Java implementations, references are actually memory addresses. Right? So references are the address of an object in memory. Right? Not all Java implementations, but many do use the address as a reference. Right? And I'll show you exactly what that means shortly. Right? So in Java, any variable whose type is not a primitive type stores a reference. Right? So in this case, this variable t, right, refers to some array list object. Right? So in other words, t stores the memory address of whatever object that is. Okay, so these memory diagrams are useful for helping you understand the differences between primitive and reference types. Right, so if you've been reading the notes, you've seen these already. Right? So a memory diagram is just a table. Right? It's got 3 columns. Right? Left-hand column, that's the variable name. Middle column is the address. Right now, every row of this table has a different address. Right? It's convenient to label the addresses starting from the top and going down in ascending order. Right? But you don't have to do it that way. All that really matters is that these addresses are unique. Right? And beside each address is a box that stores a value, only one value. So you can only store one value per box. Okay? Right, okay, and no 2 object, yeah, so you can only store one thing in a box, which means you can't put 2 things in a box, right? So for example, right, here I've got 2 lines of code, right? The first line has a primitive value called x, right? The second line defines a reference type called t, right? So what's in memory? Well, when you make the double variable x, right, you get a variable called x somewhere in memory, right? You can put it anywhere that's unoccupied, right? So it doesn't have to be on line 100. It could be anywhere for our purposes, right? And beside that value x is stored the value -1, right? So primitive values actually store primitive values store their actual values, right? If this was a Boolean variable, that could be true or false, right? If it was an int, it could be 1, 2, 3, 4, 5, or something like that, right? Now, what does a reference type store? So here's the variable t, right? Inside that box, there's a memory address, right? And a memory address, you can see, is just an integer value, right? So I need some way to write that address. So I always stick an A at the end to indicate that's an address, right? So that says that's the reference to the object that resides at address 700, right? Now, what does that mean? That means at address 700, there has to be something sitting there, and it has to be an array list object. Right? So sitting at address 700 is the beginning of some array list object. Right? I don't know how much memory it takes up. Right? I don't know where the memory for that object actually is. Right? I know that it starts at 700, but I don't know where the rest of it is. Right? And it doesn't matter for our purposes. Right? All that you care about is that somewhere in memory there's an object. Right? And that reference t refers to that object. Right? Now, you don't often see memory diagrams drawn like this, right? They're not normally shown as tables in most textbooks. Instead, what textbooks do is they draw blobs, right? So for example, is this going to work? Yes, okay. So if I want to draw a representation of those 2 lines of code, you can draw something like this, right? So you can draw a blob, right? This is going to be x. Oops, sorry. Right? So that's my blob x, and its value is -1. Right? And now, what's t? Okay, so t, there's some blob. Oh, that's not a very good t, sorry. All right, I'm just going to leave it as that. Okay, and then there's an object somewhere else in memory. Right, so there's an array list object. Right? And this thing t points to that object. Right? And that's the way you normally see it in a textbook. Right? So if it's a primitive type, right. Right? So if it's a primitive type, right, the primitive type stores the value. Right? So in other words, x is the value -1, or right? If you modify x, you modify that value. Right? If it's a reference type, then t refers to some object. Right? If you assign a new object to the reference, right, then what happens is oh, come on. There we go. Right, so if you write t equals some new array list object, then what happens is this reference points to a new object. Right? Now, that object there, right, if it has nothing pointing to it, right, so if there are no references to this object, right, then this object can go away. So the Java garbage collector can come along and get rid of that object now and release whatever memory is associated with that object. Right? So that's how objects die in Java. Right? When an object has no references referring to it, when there are no references to an object in your program, right, that object can then be removed from memory. Right? So in other words, you can reclaim whatever memory is associated with that object, and what other resources are associated with that object. Right? So that is the death of an object in Java. And you have no control over that as a programmer. Right? You have no guarantees over when the memory that's allocated to that object will actually go away. All right. Okay, so the programming you did in CISC121 and CISC101 was something called procedural programming, right? Probably in CISC121 more so than 101. You focused on taking your program and decomposing it into functions, right? So you wrote a bunch of functions, and then you called your functions, right? You passed information or data to the functions, and the functions did something with that data, right? Object-oriented programming focuses on decomposing your program into objects that interact with one another, right? Inside those objects is information or data, right? And the objects can operate on their own data, right? So it's a different way of structuring your program, right? Procedural programming, you structure into functions. Object-oriented programming, you structure into objects, right? Where the information lies is different in both types of programming. In object-oriented programming, there are four main elements, right? So there's something called abstraction, something called encapsulation, and something called modularity. Okay? There's a fourth one called hierarchy, but we're not going to get to that until part 3 of the course. Right, so we want to look at the first 3 right now. Okay, so what is abstraction? So this is a quote from a very well-known object-oriented programming expert. Right? The important parts are shown in red. Right? So he starts out by saying abstraction is one of the fundamental ways that we as humans cope with complexity. Right? And abstraction denotes the essential characteristics of an object that distinguish it from all other kinds of objects relative to the perspective of the viewer. So there's a whole bunch of things there, right? And most people forget that it's the second part most people forget that the second part is here. So it's relative to the perspective of the viewer. Right, okay, so we all, who has a driver's license here? Most people? Yeah, so it's still true that most people in Canada get their driver's license, although it's fewer and fewer all the time. So look, you all have an abstract idea of how to drive a car, right? You know that you can get in, you turn the key, you know you've turned the steering wheel left and you're pressing on the accelerator, you're going to go left, right? But I suspect none of you actually knows how the car does any of this, right? So imagine if you had to drive a car and you wanted to turn left and you had to figure out, okay, exactly how many degrees do I have to turn this wheel to make the steering wheel, to make my wheels turn 15 degrees to the left, right? Given that I'm going 45 kilometers an hour over a bumpy road, right? Your car does all of this for you, right? A modern car does anyway, right? So you have this abstract idea of how to drive a car, right? You don't worry about all the complexities of how the car actually does what it's doing, right? And you wouldn't want to know exactly how this car is doing what it's doing, right? And you wouldn't want to have to control all of this while you're trying to drive your car because you simply couldn't do it, right? So we use abstraction every day, right? Now, there's a second part here that's relative to the perspective of the viewer, right? So this is really, when he's talking about abstraction, he's talking about this in the sense of software, right? So if I now said to you, please implement a car class, right? The first thing you should ask is, well, what should the car class do? Right? In other words, who's going to be using that car, right? And what are they going to be using it for? Right? Because the way you implement that class is going to be very different depending on what you're going to use it for. Right? So for example, if you're going to be using this class to sell used automobiles on the internet, right, there's certain things you're going to want to put in that class. Right? What does the car look like? How old is it? Blah, 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 blah. Right? But if you're making this car class for a video game, then you care about a completely different set of, you care about a completely different abstraction, right? You want to know how fast can this car go, right? How fast is the car going right now, right? How can I steer it, and things like that, right? So the second part's really important, right? When you make a class, you have to consider why are you making that class and who's going to be using it, right? Because you can have entirely different classes named the same thing, right? Depending on what you're going to use them for. Okay, so encapsulation is the process of compartmentalizing the elements of an abstraction that constitutes its structure and behavior. So for structure, right, you should think information, right, or data. Behavior, for Java, you should think methods. Right? So encapsulation serves to separate the contractual interface of abstraction from its implementation. In other words, right, when you make a class, you should give it an interface. In other words, you should give it some methods that the user can call. Right? Those methods should be separate, or the user shouldn't have to know anything about how the class is implemented in order to use those methods. Right? So there should be this boundary between the user of the class and the contents of the class, right? Or not necessarily the contents, but how the class is implemented, right? All the design decisions that you made to put into this class, the user shouldn't be able to figure that out, right? The reason you want to do this is because later on you may decide that you have to implement this class in a completely different way, right? If the user knows how the class is implemented, they may have taken advantage of that knowledge when they were using the class before. If you then change how the class is implemented, what the user was doing no longer works, right? Because they took advantage of information they shouldn't have had. Right? So you're always thinking about what's the interface that I'm going to give to this class, right? And finally, there's modularity, right? Which is the act of partitioning a program into individual components, right? So in object-oriented programming, right, one of the partitionings is that you break your program down into separate classes, right? You don't make one big class that's got everything in it, right, that has the functionality of your program, right? You instead break that program down into separate objects or separate classes, right? And then create objects of those classes and let them interact, right? Now, why do you want to do this, right? So one of the reasons is to reduce its complexity, right? So imagine a program like PowerPoint, right? You could conceivably write a single class that represents the program PowerPoint. You wouldn't want to, right? It would be enormously complicated. But if you start to break that program down into individual pieces, it becomes more feasible to actually implement. Right? He goes on to say that it creates a number of well-defined documented boundaries within the program. Right? These boundaries, or there's that word interface again, right, are invaluable in the comprehension of the program, right? So again, imagine that your PowerPoint program was one class, right? And whoever implemented that class went off and died, right? And now some poor programmer has to come along and try to figure out what was going on inside this one class, right? That's going to be an enormously complicated task. But if the program is broken down into small individual pieces, right, it's now possible for other people to come and understand the individual pieces. Okay, so those are the three things that we need to keep in mind as we move forward. Right? Now, how do you actually go about, or what does an actual Java program look like? Right? Because you haven't actually really seen one. You've seen a simple one in assignment 1. Right? But a more typical Java program consists of one or more files. Right? So if it's a small program, you might just have one file, right? One or two. Right? If it's a large program, you may have thousands or tens of thousands of separate files. Right? Inside each file, right? Is it 0 or 1 package name? Right? So packages, which I'll describe in a second, that's one component of modularity in Java. Right? Then you may have 0 or more import statements. Right? So you use an import statement when you want to bring in the functionality of another class. Right? And then you typically have one class, but that's not necessarily true. But typically there's one class. Right? So every .java file typically has a single class in it. Right? Inside that class, there's some information. Right? So the information lives in what are called the fields of the class. Right? There's why did I say one or more? That can be 0 or more. There doesn't have to be one in there. Usually there's at least one though. Right? Then there are these things called constructors. Right? You know what I've told you what a constructor is for. Right? So you know that you call a constructor to make when you make an object. Right? The constructor initializes the state of the object. Right? When you go to implement a class, you have to define how is the state of the object initialized by the constructor. Right? And then finally, you've got 0 or more methods. Right? And so the methods are the actions that your objects can take. Right? Right? And there's typically many of these files in your Java in a Java program. Right? And this isn't actually the whole story. Well, here's a picture of what a class looks like. Right? So if you're reading the notebooks, you've seen this class. Right? This is the stack class. I don't care how it works right now. Right? We just want to look at the structure. Right? But when you open up a Java file, this is what you typically see. Right? At the top, you might see a package declaration. Right? Then you might see some import statements. Right? Then you'll see a class. Right? When you look at the class, you might see some what look like to be variables. Right? And that's all these really are. They are variables. Right? Then there can be some constructors, and then there can be some methods. Right? So that's what when you open up a Java file, that's what you should expect to see. Right? When you open up a real Java file, you should expect to see a whole bunch of documentation as well. Right? But it's not shown on this slide. Okay? Again, the actual contents of this file don't matter for us right now. It doesn't matter for us right now. And it's actually way more complicated than this. Right? So there's a whole bunch of things that we have no time to talk about in this class. Right? You can have things, well, I'm not going to describe all these. Right? You can have all of these things and more in an actual Java program. Right? Some of these things we'll get to. So classes inside of classes, we'll talk about that. Right? But the rest of this, I don't think we will. No, so we're probably not going to do any of this other stuff. But all of this other stuff can exist in a Java program. Right? There's a link here if you want to read a little bit more about this on your own time. Okay, so what are these packages? So packages are used to organize Java classes into what are called namespaces. Right? So this is one of the mechanisms that Java uses for modularity. Right? You want to break your program down into understandable chunks. Right? So one way to do that is to separate your classes into individual packages. Right? So the definition, this is straight from the Java language specification. Right? It says packages are used to organize Java classes into namespaces. Right? And then you ask yourself, well, what's a namespace? Right? A namespace is just a container for names. Right? And a namespace also has a name. So a namespace is just a bunch of names. Right? And there's some sort of organization of these names. Right? So packages are used to organize related classes and interfaces. Right? So everything that's in the Java standard language lives in a package called Java. Right? And then inside a package, you can have more packages. Right? And you saw this in lab 2. Right? So inside the Java package, there are packages like lang, util, IO, and many, many more. Right? Each one of these packages, right, groups together classes and other stuff that are related to each one of these things. Right? So in lang, that's all the stuff that's fundamental to the Java language. Right? In util, that's stuff that's useful. Right? So utility classes. In I/O is stuff that's related to input and output, right? So reading and writing stuff to disk or network or something else, right? Okay, now you've got a package inside of a package. So the full name of a package, right? We say the fully qualified name is just all of the packages stuck together with periods, right? So the full name of lang is actually java.lang, right? The full name of util is actually java.util. And the full name of I/O is actually java.io. Right? Inside a package, you can have classes and interfaces. Right? So You can have packages inside of packages. You can have classes inside of packages. You can have interfaces inside of packages. Right? Inside Java Lang are the fundamental Java classes, right? The ones that are most important to the language. So string is in there, for example. Right? Math is in there. This thing object, which we're going to see a lot of, is in there. Right? Now, what we call the fully qualified name of an object is all of the package names in front of the object name. Right? So java.lang.object is the fully qualified name of object. Right? Java.lang.string is the fully qualified name of string. Now, why are we going to all this trouble? Right? It's because you need to ensure that fully qualified names are unique in your program. Right? You cannot have two fully qualified names in your program. Two fully qualified names that are the same in your program. Right? The reason you can't have two of the same fully qualified name is because the compiler needs to figure out exactly which class do you mean when you say something. Right? So for example, if you just say string, you get java.lang.string in Java, right? But if you decide to make your own string class, for whatever reason, right, then you're allowed to do that, as long as it doesn't have the same fully qualified name as java.lang.string. So for example, you can create your own package called your. Inside that package, you can define the class called string, and now away you go, right? So now you can write your string s equals new your.string. Right, hello, for example, right? And in the same program, you can also use java.lang.string by writing string, right? So now you've got two classes with the same ordinary name, right? But they have different fully qualified names, so you're able to use them both in your program, right? So fully qualified names have to be unique. Okay, so that's all the fundamental stuff. Oh, wait. I must have skipped over something here. Okay, so how do you ensure that fully qualified names are in fact unique? Right? So there's what's called a package naming convention. Right? So packages should be organized using your domain name in reverse. Right? So for example, the computing science domain name, this is your internet domain name, right, is cs.queensu.ca. Right? And there is a central authority that ensures that internet domain names are unique. Right? So this is Java's way of trying to force uniqueness of package names. Right? So all you do is you reverse the order of the pieces of your domain name. Right? So for example, the package name for the computing science department at Queens would be ca.queensu.cs. Right? And if you look at the source code in the notes, right, you'll see that all of the packages start with ca.queensu.cs. Right? Good. Okay. So now we're going to talk about classes. So I told you a class is an implementation of a type, right? It's actually an implementation of a reference type in Java, right? Normally you use a class as a blueprint to make objects, right? So normally the class, when you create an object, right, you need a class to make an object, right? It's that class that's used as a blueprint for the objects themselves. And why do you want objects, right? Because every object has its own copy of all of the non-static fields inside the class. Right? What does that mean? It means every object has its own set of variables, right? Where those variables can store information, right? So that means every object gets its own state, right? Where the state is just the set of the current values of all of its non-static fields. Right? So in other words, every object's got some variables. The state of the object is just the value of those variables. Right? That's the easiest way to think about it. So we saw this point2 class last week. Right? If you have a class that lets you make point2 objects, then every point2 object can represent a different point. Right? So for example, right, I can have P, Q, and R. Right? They represent 3 different points. Right? The first point has coordinates 1, 2. The second point has coordinates -3 and 8. And the third point has coordinates 5 and 13. Right? And they're all distinct objects Right, so P, Q, and R, here are the variables. Right? Somewhere, what does P refer to? Well, it refers to this object living at address 600. Right? So you wander off to line 600 of your table. Right? And what do you find there? You find a .2 object. Right? If you were to look at the memory associated with that object, right, you'll see that it has a field called X and a field called Y. Right? So in other words, that point object's got two variables, X and Y, that happen to store the coordinates of that point. Right? What's Q? Well, Q is a new point. Right? So Q refers to the object at address 700. So you go off to line 700 of the table, and you find that there's a point object there. Right? And that .2 object has its own copy of X and Y. Right? I guess I missed a point here. That class is also sitting in memory. So when you use a class for the first time, so when you use the .2 class for the first time, it gets loaded into memory. Right? Inside the .2 class, you can see that it has two fields called X and Y. Right? So every time you make an object, you get copies of these fields X and Y. Yeah? So what do you ask? So there's both, right? So all of these objects are reference types, right? But their fields X and Y, those are all primitives. Right? So there's actually both things going on here. Okay, and finally, R, well, that's a new point, right? So if you go into the memory diagram, you see that there's R refers to the object at address 800, right? You wander over to line 800, and you see there's a .2 object whose coordinates are 5 and 13, right? These coordinates and these coordinates and these coordinates, right? They all belong to different objects, right? So if you use P to modify this point object, right? It's these two values that change. Right? If you use Q to modify this point object, right? Then it's these two values that change, right? And finally, if you use R to modify that point object, it's those coordinates that change. Right? Every object gets its own state. Okay, so many classes represent different kinds of values. Right? So examples of values are things like names, dates, colors, points. Right? In Java, examples of classes that represent values are strings, string, date, and integer. Right? String represents a sequence of characters, date represents a date, and an integer represents an integer value. Right? Okay, now how do these, what do you need to do when you go to start to implement one of these classes on your own? Right? So one of the first things you need to do is you need to decide what information do you need to represent this value. Right? So to represent a point, right? At a minimum, you need to, a two-dimensional point, at a minimum, you need to be able to represent the coordinates of the point. Right? So at a minimum, you need two fields. At a minimum, you need some way to represent the values of X and Y. Right? So you need to decide which variables you need to represent the state of an object. Right? Now, these variables have a name in Java. They're called fields. Right? Okay. So for a two-dimensional point, right, how can you represent X and Y? Right? So this is one way. Right? You can have one variable called X. You can have another variable called Y. Right? That certainly works. It's not the only way. Right? Right? It's not the only way. Right? So another way you could do this is you could have an array of length 2, right? Where the first array element represents the X coordinate, and then the second array element represents the Y coordinate. Right? Depending on why you're making this class, you could choose different types for X and Y. Right? They might be int, if you only care about integer coordinates. Right? If you care about real valued coordinates, they're probably double. Right? If you care about string coordinates for some reason, you might use strings. Although that would be unusual. Okay, so let's roll with two separate fields instead of using an array. Right? So when you make your class, right, there may be a package, right? This happens to be in that package, right? It's very long, right? But that's so I can organize all of the class notes, all of the classes that are used in the notes in a sensible way. right? Then there's what's called the class declaration, right? So in the class declaration, you give your class a name, right? Here I've called it big P.2, right? It's a reference type, so its name begins with a capital, right? It's a class, so that's what the keyword class means, right? And then there's this word public in front. So public is what's called an access modifier, right? If you have a public class, then anybody can use this class, right? And for most, I'm not going to say most. For many purposes, when you're creating classes, the classes will be public, right? Because you want other people to use them, right? So anybody can use this class. So any client can use this class, right? Now, we've decided what information should live in the class, right? So we add the fields to the class, right? And these look just like variable declarations in a method, right? So double x says there's a field called x, whose type is double, right? Double y says there's a field called y, whose type is double. But there's also an optional access modifier on the fields of your class, right? So here I've got the word private in front of these two fields, right? So what's a private field? So a private field means that only the class itself can use the variables x and y, right? So only x and y are usable as names only inside of this class, right? So if I give this point class to somebody, right, they cannot, so whoever's using the class cannot go in and modify x and y directly, right? Because they don't have access to it because they're private, right? Okay, so what did I just do? I made what's called a top-level class in Java, right? So a top-level class is a class that's not inside of another class. So for our purposes, for the next several weeks anyway, everything's a top-level class, right? A top-level class is allowed to have either no access modifier, right? So in other words, that word public doesn't have to be there, right? Or it can be public, right? So the public access modifier means that the class is visible to every other class, right? In other words, anybody can use the class, right? If there's no access modifier, it's what Java calls package private. So the access is said to be package private. What does that mean? It means the class is visible only inside of its own package, right? So only inside of its own package is that class actually usable, right? So for now, everything's going to be public because we want to be able to use these classes freely, right? Later on, you'll see why we choose to make some classes package private. Okay, now what about the fields? So fields are allowed to have 4 different access modifiers, right? So private means the field is visible only inside the class itself, right? No access modifier means that the field is package private, right? So that's the same, I have to be careful with this one. Same as private, and field is also, so package private means that the fields are visible to classes inside the same package, right? Protected means the same thing as package private, so any class in the same package can see those fields, but it's also visible to all the subclasses of the class, right? Now, we're going to deal with that in part 3 of the notes. So ignore protected for now, right? You can actually ignore package private for now as well, right? And then a public field means that the field is actually visible to all classes everywhere, right? So for now, the 2 important ones are public and private, right? Private means the field is only visible inside the class itself. Public means the field is visible everywhere. Okay, so what should you do when you put an access modifier on a field, right? So for now, any field that represents a constant value, right, can be public, right? So for example, the value pi, capital Pi in java.lang.math, right? That's, if you look at the documentation, it'll say public in front of it, right? So the value pi is a public field in the class called math, right? Why is it public? It's because the math class wants people to use that value for pi, right? It's actually providing you the value for pi that you can use in your programs without having to type it in yourself, right? It has to be public in order for everybody else to use it. Okay, if it's not a constant, it should be private, right? At least for the time being. So when you create your fields in your class, right, for the most part, they're going to be private, right? Package private, we'll talk about a little later. Protected appears in part 3 of the course. Okay, what do we got here for time? Okay, so I want to start to implement so I'm going to try to start implementing very, very simple classes, right? The simplest class that I could come up with is a counter class, right? So I just want some object that can count, starting from 0, right? And counts up. That's all it can do. All it can do is count up, right? So this is about as simple a class that you can make. Oh, wait. What fields do you need to represent a counter, not a point? Right? So I want something that can count in integer increments upwards. Right? So what information do I need to store inside of this class? Right? Well, I need something to store the count. Right? So I need something that I can use to store the value or the count of the counter. Right? Okay, so again, I've got a package name up here. Right? I've got a class called counter. It's public, right? So anybody can use this class, right? What information do I need, or what fields do I need? Well, I need the value of the counter, right? So I'm going to use an int in this case, and I'm going to make it private, right? How about a stopwatch? Right? So now I want a class that represents a stopwatch, right? So you can start the stopwatch, you can stop the stopwatch, right? And the stopwatch tells you how much time has elapsed between pressing start and stop, right? Oh, I keep on making this mistake. What fields do you need to represent the stopwatch, right? So now you have to think about this for a little while. You say, well, right? You think about it a little while longer, and you say something, right? Okay, so how do you go about doing this? You probably don't know how to do this because you don't know how to get time from Java, right? To get the current time, you can use this method called nanotime that lives in the system class. Right, so nanotime tells you, it gives you the most precisely available system time in nanoseconds. Right? And it tells you this time relative to some fixed but arbitrary time. In other words, you don't actually know what 0 time means. Right? It doesn't tell you. Right? You just get back some long number. Right? Now, to get the amount of time that's passed, right, you can just call nanotime twice. Right? So you call it once when you want to start timing. You call it again when you want to stop timing. And the amount of time that's passed is just the stop time minus the start time. Right? And it gives it back to you in nanoseconds, so 10 to the minus 9 seconds. Okay, so how do you go about implementing this thing? There's lots of ways to do it. Right? Lots of ways to do it. So the way I'm going to do it, though, is I'm going to record what the time is when you start the stopwatch. Right, so that's my raw start time. It's raw because it's in nanoseconds, right? And I want to convert everything to something else later on. Right? It's long because that's what nanotime returns, right? So you have to go and look at the documentation for nanotime and find out what it returns. It's private because I don't want anybody coming in and fiddling with that start time, right? I want to keep that private to the class. Right? I'm going to record the stop time of the timer, right? So that's when you press stop. Right? And then I'm going to have a field that tells you whether or not the stopwatch is running. Right? So this is false if you haven't pressed start yet. Right? It's false when you press stop. But when you press start and you haven't pressed stop yet, that's true. Right? So you know that the stopwatch is running. Right? And so that would be one way to represent the information that you need to implement a stopwatch class. Okay, our classes don't have anything in them, right? We've got the class, we've got some fields, and that's it. There's no methods, there's nothing, right? But somewhat surprisingly, they're usable, right? In their current form, you can actually use them, right? So you can make objects. You just can't do anything with the object. Well, you can't do much with the objects that you make, right? So if you write this little class, make some objects, right, and you import, there's a missing thing here. That should be dot counter dot capital counter, right? If you actually write this class and run it, it will run, right? So you can, in fact, make a point, even though there's nothing in our point class except a field x and y, right? You can make a counter, even though there's nothing in the counter class except the value. And you can make a stopwatch, even though there's nothing in the class except for 3 fields, right? This actually works, which is surprising, right? Because it doesn't look like we've defined a constructor in any of these classes. Okay, but we'll get to that in a moment. Do I want to start this? I don't think I want, hang on, just let me take a quick look. Okay, so I'll talk about this slide and then we'll stop there, because there's actually been a lot of information that's thrown at you today, right? Okay, so we can add features to our class to make them more useful, right? So I can make these objects, but I can't do anything with them yet, right? So how do I make these things, how do I make these objects do stuff? Well, you add methods to the class, right? What are the methods going to do? Right? So the methods are going to use the fields to do something, right? And that's why you put information into your objects, right? All your methods will operate on that information, right? So for example, in the stopwatch class, right, I can add some sort of method that lets me start the stopwatch. I can add some method that lets me stop the stopwatch. And then I can add some method that tells me how much time has gone between start and stop, right? And then I can do other things as well, right? So I can add constructors to the class, right? What do the constructors let me do? Or what do the constructors let a user do? They let the users set the values for the fields, right? So I can add a constructor to the point2 class that lets the user specify what the starting x and y coordinates of that point should be, right? So in object-oriented programming, the term encapsulation, right, which we just talked about a little while ago, right? What does it mean? It really means bundling data and methods that use the data into a single unit, right? Often the units in Java are classes, right? So every class has information in the form of fields, right? It's got behavior in the form of methods, right? And those are all grouped together in one place called the class. Okay, and with that, I will end the lecture. And I guess I'll see you on Monday, right? Sure.